In this part of the Neurocomputers and Deep Learning course related to associative memory, you will learn how to implement accretive auto-associative memory using discrete Hopfield network. In this section, we will investigate how Hopfield network can be used as auto-associative memory. For this purpose, some modifications are done on continuous Hopfield network so that it works in discrete state space and discrete time. Here is the Hopfield network as given previously. We want to use it as associative memory, and instead of the tangent hyperbolic output function, we will use a special case of that function where the slope at 0 is infinity, so this becomes the shifted threshold function. So this is called sine function. Note that whenever the patterns to be stored in Hopfield network are from n-dimensional bipolar space constituting an hypercube, that is, UK is a vector of size n, and each component is either -1 or 1. For k from 1 up to capital K. Then it is convenient to have any stable state of the network on the corners of the hypercube. If we let the output transfer function of the neurons in the network to have very high gain in the extreme case, when k goes to infinity, limit tangent hyperbolic Ka is equal to Fia, and here Fia in the limit case is equal to sine A, which is 1 for A greater than 0, 0 for A equal to 0, and -1 for A less than 0. Furthermore, note that the second term of the energy function, which was given in chapter 2 previously, this term approaches to 0. As the slope at the origin goes to infinity, the integral from 0 to xi, the inverse of the function, approaches to 0, so this second term disappears. Therefore, the stable state of the network corresponds to the local minima of the function. Here, the second term removed, so we have this double summation here and also the last term. In the double summation, we are considering each pair of the neuron outputs, and we are considering the connection between them. For each I and j, we are considering this summation. At the end, we are multiplying with -1/2. And for this one, these are the theta values of each neuron multiplied by the output of the neuron. I is from 1 to n. So that they lie on the corners of the hypercube as explained previously. Remember that the Hopfield network defined previously in chapter 2 was continuous Hopfield network, which has tangent hyperbolic as the output function, and it is a continuous function. It's a continuous space network. Also, the dynamics of the continuous Hopfield network was defined as a differential equation, so it is also continuous in time. However, for the Hopfield auto-associative memory, we are considering discrete time state excitation, so it is defined as the output value of the ith neuron in the state vector at time k plus 1, so for the next time, is equal to the function f applied on the activation value of the neuron I at time k, which is defined as the output value is 1 if the activation of the ith neuron at time k is greater than 0. It remains the same if the activation of that neuron at time k is equal to 0, and it is assigned value -1 if the activation of that neuron is less than 0, where AIK activation is defined as we used to, that is, activation I at time k is equal to summation j from 1 to n. We are constant the connection weight from the neuron j to our neuron I. We are multiplying it with the output of the j neuron at time k plus theta I. The processing elements of the network are updated one at a time, such that all of the processing elements must be updated at the same average rate, called asynchronous update or sequential update. For stability of the bipolar Hopfield network, it is further required to have Wii equal to 0 in addition to the constraint Wij equal to Wji. So there is no self-connection in the Hopfield network for the discrete case. In addition to symmetry in the connections, there is no self-connection in the discrete Hopfield network. In order to use discrete Hopfield network as auto-associative memory, first its weights are fixed to W is the weight matrix, which is equal to U transpose by definition, where U is the input pattern matrix as defined in this equation previously. Here U is the matrix having k columns. These are the exemplars to be remembered by the Hopfield associative memory, and each column here is a vector of dimension n. Remember that the matrix U is such that here each column is one of the exemplar to be remembered, and each exemplar is of dimension n, where U is the input pattern matrix as defined by this equation. Here each column is corresponding to an exemplar to be remembered, and each exemplar is of dimension n. After calculating U transpose, we are setting each diagonal entry Wi to 0. Remember that in auto-associative memory, we have Y equal to U, where Y is the matrix of desired output patterns as defined in this equation. So it will remember these stored patterns as the output. If all the states of the network are to be updated at once, it is called synchronous update or parallel update. Then the next state of the system may be represented in the form the state vector. This is the vector where each component is the output of the corresponding neuron in the network, and state vector k plus 1 is equal to the f function that we defined previously for the discrete case, applied on weight matrix transpose multiplied by the state vector at time k. For the special case, if the exemplars are orthonormal, we have f applied on W transpose UR. This is the state at time 0. We are setting x0 to UR. Notice that if the patterns are orthonormal, then weight transpose UR is equal to UR itself. Then, if f is applied on UR, we are considering each component of the vector, because the function f is such that if the value is negative, then the value of the function applied on that value will be -1, and if it is positive, the value will be +1, because here in the u vector there is no value as 0, so all the output values obtained are either -1 or +1, and they are the same as in the vector itself. Because of that, at the output, we will see Ugur. That means that each exemplar is a stable state of the network if the input patterns are orthonormal. Whenever the initial state is set to one of the exemplars, the system remains there. However, if the initial state is set to some arbitrary input, then the network converges to one of the stored exemplars depending on the Bayesian attraction in which x0 lies. However, in general, the input patterns are not orthonormal, so there is no guarantee that each exemplar is corresponding to a stable state. Therefore, the problems that we mentioned previously arise. The capacity of Hopfield network is less than 0.138 multiplied by n patterns, where n is the number of units in the network. It should be noticed that the energy function of the discrete Hopfield network, which is a special case of the continuous Hopfield network, as the state of the processing elements are changed one by one for the asynchronous update.